this video, we will talk about relations. So basically, we'll start with Cartesian product, we will extend the concept to relation, and we will also discuss various types of relations. Cartesian product we have already discussed in earlier videos, but I'll just give you the recap. Cartesian product is defined over sets A and B as follow. A Cartesian product B is given by set of all the ordered tuples A comma B such that the element small a is coming from first set, that is capital A, and second element small b is coming from second set, that is capital B. So Cartesian product is ultimately a set which contains ordered tuple where first element must be from first set, second element must be from second set. Let's consider A is ABC and B is equal to 1, 2. To compute the Cartesian product between these two sets, we have to associate each element of set A with every other element in set B. So A Cartesian product B would be A1, B1, C1, A2, B2, C2. As you can see that all the first elements in all the tuples are coming from first set capital A shown in red, and second element is coming from second set B shown in blue. And Cartesian product itself is a set, and we know that set is an unordered collection of elements, so we can definitely shuffle the order of tuple inside. So A Cartesian product we can also write as A comma 1, A comma 2, B comma 1, B comma 2, C comma 1, C comma 2. We can also write it as a C1, C2, A1, B1, B2, A2, any order is possible. But we cannot alter the order of elements within the tuple. So we cannot have 1 comma A, 2 comma A, because here the first element in tuple is coming from set B and second is coming from set A. So this is actually B Cartesian product with A. This proves that A Cartesian product B is not same as B Cartesian product A. Let us compute power set of A Cartesian product B. So first we'll compute Cartesian product between two sets A and B. As there are only single elements, the Cartesian product will have only one entry, that is A comma B. And the power set of that set would be phi and the set itself. Because if set is having one element, then power set will have 2 power 1, that is 2 elements. In general, if set is having n elements, power set contains 2 power n elements. Let us extend the concept. Compute power set of A Cartesian product power set of B. So first we need to compute power set of A and B, and then we will take the Cartesian product between those two sets. Power set of A is phi and element A, and power set of B is phi and set element B. As we can see, power set of A and power set of B both contains 2 elements, so the Cartesian product will contain 4 elements, where the first element will be from power set of A and second element would be from power set of B. So that would be phi comma phi, phi comma B, A comma phi and A comma B. Concept of Cartesian product we can easily extend to multiple sets as well. So if A cross B cross C is given, then we can write the Cartesian product as triplet now. Instead of 2 elements, now we have a triplet, 3 elements, small a, small b and small c, such that small a is coming from first set capital A, small b is coming from second set capital B, and third element small c is coming from third set capital C. Order is very important. Technically, we can write A Cartesian product with B Cartesian product C is same as A Cartesian product B, and then we'll take the Cartesian product of that set with C. So let us consider the example A Cartesian product B comma C Cartesian product D. So first we'll compute the Cartesian product between first two set, so that is given by A comma B and A comma C. Fine, and then we'll take the Cartesian product of that with the third set, that is D. So that will be first element from the first set, that is AB and comma D, and then second element from the first set AC and comma D. And we will drop unnecessary parentheses. So ultimately we have 2 elements ABD and ACD. Relation is defined over the Cartesian product of the sets. Now these sets can be either same or it could be different, that depends on to the relationship. So normally the binary relation is defined over two sets. We can have a tertiary relation over three sets and so on. Formally, we can define binary relation on set A and B as a collection of all ordered pairs of element of A cross B. So A cross B is a Cartesian product between these two sets. Generally, the relation is represented by capital letter R, and if the tuple A comma B is in relation R, then we can also rewrite it as a ARB. So Cartesian product contains all the possible combination of elements of two sets, but relation may not be true for all. So relation would be typically subset of the Cartesian product of two sets, because for relation certain conditions are imposed and only those tuples will be in relation which satisfies those conditions. So if set A is having cardinality m and set B has cardinality n, then there exist 2 power mn relationships over these two sets. Consider the example of person and contact number. Let's say capital P represents 3 person, P1, P2, P3, and capital C set represents their corresponding contact number C1, C2, C3. So person P1 has contact number C1, P2 has contact number C2, and P3 has contact number C3. The Cartesian product of these two sets would be of cardinality 9. That means there would be 9 elements because cardinality of P is 3 and same of C is 3. So there would be 3 into 3, that is 9 elements. But all will not hold the relation because we know that every person is associated with one contact number only. So when I find the relation PRC, that means the person is having particular contact number. So that will only contain 3 tuples P1, C1, P2, C2, P3, C3. So we can say that relation is here subset of the Cartesian product. Consider the less than relation over the set of natural number. So set of natural number is 1, 2, 3, 4, 5 up to infinity. And when we take the Cartesian product, we will have again infinite tuples 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 4, 3, 4 and so on. It goes on. But all those elements or all those tuples will not be in this less than relation because certain tuples do not hold that relation. For example, 1, 1. So here the first element is not less than second element, so that is not in the relation. If we consider rest of all the elements 1, 2, 1, 3, 1, 4, 1, 5, so definitely here A is less than B. That is first element is less than second element. So all shown in black are in relation. Then we'll take the combination with 2, 2, 1, 2, 2, 2, 3, 2, 4 up to 2 infinity. So 2, 1 and 2, 2, they are not holding the relation less than because here A is not less than B. 2 less than 1 is false, 2 less than 2 is also false. But for remaining all the tuples, it is true. For combinations with 3, 3, 1, 3, 2, 3, 3, they are not in relation, but 3, 4, 3, 5, 3, 6 up to infinity, they will be in relation. So approximately we can say half of the elements in this particular relation, in this particular Cartesian product are in relation because the members will be increasing in every line. The non-members are increasing in every line. So 50% of element will be in relation, 50% will not be. Often relations are defined over the same set. That is, we can say that R is a subset of A Cartesian product of A. For example, addition of natural number. So when we add 2 natural number, it will produce the number which is again in the set of natural number only. Not all relations are over the same set. For example, relation describing prices of computer component. So hard drive is having price $55, RAM is having price $49, DVD has price $1. So you see that element A is coming from the set of components, whereas element B is coming from set of prices. So here relation is defined over 2 different sets. Let us discuss various types of the relation. The first one is the reflexive relation. A binary relation on set A is said to be reflexive if for all the elements in A, set A, if that element is related to itself. That is, R should contain tuple A, where A is member of capital A. For example, if our set A is 1, 2, then reflexive relation would be 1, 1 and 2, 2. Then we can say that this relation is reflexive. Another example of reflexive relation is vertex u is reachable from vertex u. So we know that every vertex is reachable from itself in any graph. So reachable from the same vertex is also reflexive relation. We can always say that u is reachable from u. So is reachable is reflexive. Is equal to, less than or equal to, greater than or equal to are also a reflexive relation. We can say phi is equal to phi, or we can say phi less than or equal to phi. We can also say phi greater than or equal to phi. So all these operators are reflexive. Less than and greater than are not reflexive. We cannot say phi less than 6 or phi less than 5, 7 less than 7, 10 greater than 10. That's false. So they are not reflexive. The transitive relation, we can say that relation R is transitive if any element A is related to B and B is related to C, then A must be related to C. That is, if a tuple A comma B is in R and B comma C is in R, it implies A comma C must be in R. If it is true for all the elements of the relation or all the tuples in the relation, then we can say that relation is transitive relation. Consider set A is 1 to 3, set B is 1 to 3, and R is equal to AB such that A less than B. Okay? So we can say that the given relation 1 comma 2, so definitely A is less than B, 2 comma 3, that is also definitely A less than B, and 1 comma 3 is also holding A comma B. Right? So all these three elements are satisfying the relation A less than B. We have to check whether it is transitive or not. So 1 comma 2 and 2 comma 3 are in relation. So 1 comma 3 must be in relation, and it is there. So we can say that R is transitive relation. For all such pairs which are in R, this condition should be true. Another example of transitive relation, if we can move from vertex U to V and we can move from V to W, then we can definitely say that it is possible to move from U to W. So this reachability property, we can reach from U to V, we can reach from V to W, so definitely we can reach from U to W via V, right? So this is reachability is also transitive relation. Is equal to, less than or equal to, greater than or equal to, less than, greater than, predecessor of, descendant of, these all are transitive relation. We can say that if 1 is less than 2 and 2 is less than 5, then definitely 1 is less than 5. And we can prove the transitivity for all these relations. Not equal to is not transitive. We can say that 3 is not equal to 5 and 5 is not equal to 3. So there should be a relation 3 is not equal to 3, which is not true. So this is not transitive. Similarly, A is equal to B plus 2 is not true. We can take appropriate values of A and B and we can always prove it's not transitive. Symmetric relation. Relation R is called symmetric if and only if A is related to B, then B is also related to A. Mathematically, we can define if tuple A comma B is in R, that implies B comma A must be in R. For example, A is 1, 2, 3 is a set. Cartesian product contains 9 tuples, but some of the tuples will form symmetric relation. Let's consider R is equal to 1, 2, 2, 1, 1, 3, 3, 1. So if 1, 2 is in R, then 2, 1 must be in R, which is there. Next 1, 3 is in R, so 3, 1 must be in R, which is there. So this particular relation is symmetric. If we can move from U to V, then definitely we can come from V to U. So that reachability is also symmetric. Is equal to being sibling is also symmetric. A is equal to B, then we can say B is equal to A. Or if we can say that if A is cousin of B, we can say B is cousin of A. So that or A is sibling of B, B is sibling of A. Right? So being sibling is symmetric, but being brother is not symmetric. Right? Or being sister is not symmetric because it could be girl and boy. So we can say that Maria is sister of Alex, but we cannot say vice versa. Alex is sister of Maria. So that is not true, right? So being brother, being sister is not symmetric, but being sibling is symmetric. In same way, less than or equal to, greater than or equal to, they all are not symmetric. That we can definitely prove with the appropriate data. Asymmetric relation. Binary relation R is called asymmetric if A is related to B, but B is not related to A. Fine. Even no AA should be in R. So make sure to understand this condition that if A implies B, if A comma B is in R, then B comma A must not be in R. And even AA cannot be in R. For example, R is equal to 1, 2, comma 2, 3. So here we can say that 1, 2 is in R, so 2, 1 must not be there. 2, comma 3 is in R, so 3, comma 2 must not be in R. If it is true for all the elements or all the tuples in R, we can say it's a symmetric. So this R is asymmetric relation. 1, 2 is present, 2, 1 is not there. 2, 3 is present, 3, 2 is not there. 1, 1 is present, but 1, 1 is not allowed in asymmetric. So this R is not asymmetric relation. Less than, greater than, father of, student of, all these are asymmetric relation. Is equal to is not asymmetric. Otherwise 1, 1 would be allowed, which is not the case. Antisymmetric relation. A relation R is said to be antisymmetric if element A is related to B and B is related to A, that implies A is equal to B. That is, if A is not equal to B, then BA must not be in R. Consider A is equal to 1, 2, 3. Then if we consider 1, 2, 2, 1, 3, 1, then it is not antisymmetric. And R is equal to 1, 2, 2, 3, 1, 1 is not asymmetric, but it is antisymmetric. We know that 1, 1 is not allowed in asymmetric, but it is possible in antisymmetric. Is equal to is antisymmetric relation, and less than and greater than are example of non-antisymmetric relation. Relation is said to be equivalence if it is reflexive, symmetric and transitive. All three properties must be hold. For example, is equal to is equivalence, less than and greater than are not equivalence. Relation is said to be partial order relation if it is reflexive, antisymmetric and transitive. And a set on which this relation is defined is known as a partially ordered set, or in short, it is referred as a PO set. Consider A is equal to 1, 2, 4, on which the relation R is defined as a 1, 1, 2, 2, 4, 4, 4, 2, 2, 1, 4, 1. To check whether it is a PO set or not, we have to apply all three conditions. It should be reflexive, it should be antisymmetric, and it should be transitive. And which is indeed, so this R is called partial ordered set. The another one is divides over n. So on set of natural number, if we define the relation divides, then that is also partial order, because it is reflexive, because every element divides itself. So that's a reflexive property. It is antisymmetric because A by B, then B by A, if and only if A is B. So if you say that 2 divides 5, but 5 divides 2 would be wrong in that case. Okay? You can divide 8 by 4, but 4 divided by 8 is not true, because we have divided that, we have defined that relation over a set of natural numbers. So real numbers or the fractional values are not possible. So 8 by 4 is true, but 4 by 8 is not true. And if both elements are the same, then only we can say that A by B and B by A are true. So this is antisymmetric. And definitely if A divides B and B divides C, then we can say A divides C. For example, 2 divides 4, 4 divides 8, so we can say 2 divides 8. So this is transitive as well. Let us test your knowledge. Give few examples of any phi reflexive relation. Give example of any phi symmetric relation. Give example of any phi transitive relation. Differentiate symmetric and asymmetric relation, and differentiate asymmetric and antisymmetric relation. If you have, you can post your answers in the comment box, and if you have any problem or query in understanding the answers, you can visit the link given in the description box where all the answers are posted. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.